Hi. In this video, I'll be walking through my Lab 4 report on the motion of a spring on a spring oscillation in 2 dimensions. I'll cover the fundamental principles guiding the analysis, how I set up the computational model, and what this tells us about the energy in the oscillation periods. So basically, this lab analyzes a spring mass system where the mass swings in an arc while also bouncing on the spring. So it's going in the x and y direction simultaneously instead of our other ones, which is just simple projectile motion. The core principle in our analysis will be the energy principle. So in a closed system made of the spring, the mass, and the earth, the total change of energy should be 0. We also rely on the momentum principle, as you can see, in Hooke's law, which tells us that the spring force equals negative k times the stretch, which is always pointing back towards equilibrium. And then, firstly, we use tracker to extract the position data from the provided spring mass video, and the tracker output, the first data was x equals negative 0.074 and y equals 0.663 meters. So to find our initial velocity, I use the first 2 rows of the position data divided by the time interval between the frames, which is about 0.095 seconds, and it gives us a Vx of about 0.445 meters per second and a Vy of negative 0.21. These values go right into the glow script codes, as you can see. Yeah. So next, we need to determine the spring constant K and the relaxed length L. So for K, is a relationship between the period of the oscillation and the spring constant. And basically, T equals 2 pi times the square root of m over K rearranges to K equals 4 pi squared times m over T squared. And since we know that m equals 0.402 kilograms, we calculate T. And we got from this a K of 7.442 newtons per meter. For L0, the relaxed length, I use the equilibrium condition, mg equals k times the stretch. So rearranging this, L0 equals the total length minus mg over k. At equilibrium, the spring length was over 0.7 meters, so L0 equals 0.7 minus 4.02 times 9.8 over 7.442, which comes out to 0.71 meters. So with these, I set up the glow script code model, and the time step delta t is set to 1 over 210 seconds, which is small enough for accurate integration and integer multiple of the frame interval. The simulation runs until t equals 9.23 seconds. So inside the main loop, the code calculates the gravitational force as a downward vector equal to m times g. And the spring force using Hooke's law, as you can see here, negative k times the unit vector along the spring. And then the net force updates the velocity via the momentum principle, and the position updates from that new velocity. The spring vector L, the unit vector L hat, and the stretch S are all recalculated at each step, as you can see here. Energy values, kinetic, gravitational, and potential are tracked throughout, as you can see at the top. Yeah, so basically, the energy principle. It is upheld because looking at the energy plot, we can see that the change in total energy, delta E, stays at 0 throughout the whole entire thing. While the kinetic energy and 2 potential energies oscillate and exchange with each other, they always cancel out. So this basically confirms that the energy principle is satisfied and our closed system conserves energy just as we predicted. So, estimating the oscillation periods. From the exposition data, we measured one midpoint crossing to the next, gives a period about 1.8 seconds. From the Y position data, doing the same analysis gives roughly 1.715 seconds, about 0.095 seconds shorter, which is 1 frame interval of difference, which is likely a tiny little tracking offset. The two estimates are very close to make physical sense. Since the mass is one system, both directions should oscillate with the exact same underlying period. Anyway, to summarize, the computational model closely matched the observed tracker data, and the energy principle was clearly satisfied, with total energy remaining at 0, and the x and y oscillation periods were in strong agreement. Thanks for watching.